Our plan to prove the Harder-Day theorem is a strange one. We are not going to do it right away. We are going to first argue what happens to this number when we reverse a single arc of D. And then once we know that it doesn't change the parity when we do that, so if it was odd, it stays odd, we are going to reverse basically everything we can in D so that the tournament becomes a lot nicer. And then we will prove the oddness for the nice tournament we get at the end. So it's a multi-step argument. Instead of proving it for original D, we keep tweaking D until it becomes nice, and then we prove it for the nice ones that we get at the end. This is not the only place where you can encounter this argument. It's one of many tricks that reappear in different places. So our tool for understanding what happens when we reverse an arc is the following. I'm going to call it a lemma. Let D equals VA be a tournament, and let VW be an arc of D. Recall VW means the pair, V, W. Let D prime be the digraph obtained from D by reversing the arc VW. So we take the arc VW and we replace it by WV. We make it flow backwards. So in other words, to be rigorous, here is what I mean. Take away VW and in WV. Then D prime is again a tournament, and this reversal hasn't changed the number of Hamiltonian pairs modulo 2. So here is our crucial lemma for the proof of the Harder-Day theorem. So here is a little picture. So what does this picture show? This picture just shows the arc. Of course, the tournament is much bigger than this, but we only look at what is changing, and the only thing that's changing from D to D prime is this little arc. So let's prove this lemma. And for that, we will need two more digraphs. So, okay, first of all, D prime is clearly a tournament because again, there is a single arc between V and W, except it's a different arc now than it used to be, but still there is one. And for any other two vertices, the answer how many arcs there are hasn't changed. So the tournament axiom is still satisfied. So it remains to prove the congruence mod 2. So I'm going to add two more digraphs into the mix. So D has an arc from V to W. D prime has an arc from W to V instead. D0 has none of the arcs, and D2 has both of the arcs. This should explain the 0 and the 2 subscripts. They're not random. So much for the arcs between V and W. All the other arcs are unchanged. So if you have any other vertex, all those arcs will be the same in all four digraphs. So let me formally describe this. D0 is the digraph D is the arcs with the arc VW removed, and D2 is the digraph D with the arc WV added. So notice that these are not tournaments, these are just digraphs. This does not satisfy the tournament axiom, and this doesn't satisfy it either.